They sent it to Einstein and asked, what exactly is your view? And here is, before I actually go into the applications of Planck's quantum theory of radiation, let me check what is the Einstein's view of Planck, such that, we can replace this word packet with something else which was introduced for the first time through Einstein. Watch carefully here before I go here and look into this. This is Einstein's view of Planck's quantum theory. Planck's quantum theory. And what is his view? Look at this. You bundle the entire page of the Nobel contention lecture where you are given Nobel Prize, and look into this guy who the lecture has been sent, and look at his view. I love it. And look the way he says. He simply says radiation. Now I want all the students who are pursuing science now, this is a statement which you need to remember till you die, and please understand that. And someone is asking you radiation when you go out and flaunt as a science student, this is what you need to remember, and forget about the entire 3000 pages of Planck's theory and the gist of what he told with some crude words like packet. Forget about all those and just understand that what is the Einstein view of Planck's quantum theory. Not only Planck, there was a precedent set up. You propose any theory, it's basically sent to what Einstein to his views, right? And look into this, how simplified it is. And I love this guy's brain, Einstein's brain, and so rational it is, so easy to understand. So watch here, radiation, according to him and according to you from now on, so should be described like this. Radiation is basically a shower. I would like to underline shower. Now what happens is, if you actually recollect the Planck's quantum theory, he was telling that radiation is shot out in a discontinuous fashion. It's not shot out quickly, the packet after packet, packet after packet, packet after packet. So the discontinuous fashion, look at the way the Einstein is describing, and Einstein says that radiation is a shower. And I think you and me have gone to shower so many times, and you look at the way the shower comes, the droplet after droplet, droplet after droplet, droplet after droplet. So look into the way the discontinuous fashion has been described by Einstein in the most simplest fashion. And look at this, radiation is a shower. It's a shower, not a tap water where the water is continuous flow. Now understand that radiation is a shower of, as I said, this packet is something which is absolutely crude. So what I will do, I will replace the term packet, which was used by Planck, and look into the way, and radiation is shower of, and look at this, photons. Now imagine, the packet has been removed. Now the packet has been synonymously substituted for photon. So I want to remind all the students that photon is a word first introduced by Einstein. The word packet has been removed and substituted for photon for the first time by Einstein. So I'm not surprised when 3000 pages of the contention of the Nobel Prize by Planck explaining the dual nature of light and proposing E is equal to h nu, the equation, look into this entire 3000 pages, and he has given only two statements, and this is what you need to remember when someone is asking you what exactly is radiation. And I think you should be smart enough to tell like this. Don't tell the entire 3000 pages lecture of Planck. And look into this. Radiation is basically a shower, indicating that it's a discontinuous way shooting out by a source of radiation, droplet after droplet, droplet after droplet. You must understand. And it's no more packet now. Forget about the packet, right? Radiation is basically a shower of photons. Now, nothing has been substituted. Nothing has been absolutely substituted for Planck. He got his Nobel Prize. But the way we describe, I think I wanted every student now who pursues science in their lifetime, if someone is asking you what is radiation, and I would like to underline that radiation is basically a shower of photons. Now coming to the main point, like now he has been telling that radiation has a dual nature. Dual nature. How would Einstein actually describe that? People will ask him, what is a photon? Suppose if I am asking you, what is a photon? What is a photon? Then he must be in a position to tell it has a dual nature. So what he is telling basically is, I would like to underline this, watch. Photon, according to Einstein, photon is a synthesis. Look into these words. Synthesis is basically an outcome. Synthesis is basically a consequence. Synthesis is basically an outcome of a certain thing. So if you ask me what is photon according to Einstein, and see what he's telling, photon is a synthesis of both wave and a particle. Remember that. I'm not changing the gist of Planck, and no one can change. No one can change because he has already received the Nobel Prize. Only thing is, what is your view? That was the habit that was prevailing at that particular point of time. Anyone can receive any prizes, anyone can propose anything, but that was bundled into Einstein to check his views. And I love this view of this guy because he says that radiation is a shower, indicating that it has a discontinuous fashion. It's going in a discontinuous fashion. Second, I have replaced the packet word with the photons, mind you. And I want all the students to now forget about a packet and remember that it's a photon. And if there is a question posed for the dual nature, according to Einstein, what exactly is it? Now understand that photon is a synthesis of both wave and a particle. It's an outcome of a both wave and a particle. So photon is basically associated with both wave characteristics as well as what? Particle characteristics, you must understand. And if you ask me, can you draw a photon? Because in our school, I think our teachers were telling us that photon is a corpuscle, and we have dreamt all these years that photon is basically a particle, and you know how to visualize a particle. Now here is something new. If you ask me, draw the photons diagram, then look into this. Look into this. I'm drawing the photon diagram. Mind you that this is how a photon will look like, crest and trough, and one crest and one trough will make a wave. So this, I call this to be a photon wave, you must understand. Photon wave. This was new. This is completely new for us because in 10th class our teachers were telling that photon is basically a particle. Now here is what I have drawn the photon for you, and this photon is not new. This is just equal to, this is just synonymous to your wave, where you have a wave will be consisting of a crest and trough. A crest and trough will make a wave, and this is how is a photon wave. Someone is asking you, can you draw a photon? Photon will not have anything else except for a crest and a trough. You must understand. This is new. So photon is a particle as well as photon is a wave. This is how is the Einstein's view. And now onwards, from this second, if you wanted to go out and ask, someone is asking you what is radiation, forget about what Planck has been telling. You be smart and just explain to him that radiation is a shower. It's a shower. It's not a tap water where you have a continuous flow. It's a shower of photons, and photon is basically a synthesis of both wave and a particle. And what is new? If someone is asking draw a photon wave, then it will be having a crest and a trough. You must understand. We will go in for an applications of quantum theory of radiation proposed by Planck. Right? Now we have divorced the word what? Packet. We are now hanging on to what? Photon. Right? And remember that photon has a dual nature. It will be functioning as a particle. It will be functioning as a wave. Now what we will do is, let's go in for an applications of quantum theory. Right? What does it have? The first application is basically the photoelectric effect. And I wanted to draw the attention of every student to understand that you will be getting at any cost 2 questions in the photoelectric effect in your aptitude tests. That's nothing but your JEE mains or any pre-engineering test or NEET or whatever. So it's very much important. I would like to actually pinpoint that what are the questions. Remember that. But I think the photoelectric effect and its equations and its applications of the Planck's quantum theory are definitely questions in exam. And now what I will do, I'll write the very first question before I actually go in for defining what is photoelectric effect. Here is the first question itself for your exam. And look into this. This is the question. Photoelectric effect. Now suppose if someone is asking you what is photoelectric effect, prima facie you tell him that it's an application of Planck's quantum theory. What is photoelectric effect? It is just an application of quantum theory of radiation. That is photoelectric effect. So what is the very first question? I quote this and I underline it's very, very important. And what is this? It is a direct proof. I quote, it's a direct proof that radiation is a particle. Now, what is the question here? Which of the following is a direct proof that radiation is a particle is a question in exam. And I have seen this question asked so many times in the exam. Remember that I think you must be putting a tick mark on photoelectric effect. And photoelectric effect is a direct proof for radiation to be a particle. You must understand this. Right? Now coming to what exactly is a photoelectric effect. So prima facie, if someone is asking you what is photoelectric effect, you just finish off by telling that it's basically an application of what? Planck's quantum theory. It's basically application of a Planck's quantum theory, and it's a direct proof that radiation is a particle. Radiation is a particle. Now what exactly is photoelectric effect? Observe carefully here. What exactly is a photoelectric effect? I would like to define it. Right? The knocking, or I call this to be extrication. If the extrication implying that it's knocking out. It's knocking out. It's a powerful word. Now remember that I can use the simplest words like what? Removal. Removal. It looks passive. It looks absolutely passive. I use a much better word. I call this to be extrication. Extrication. And for a synonymous view, what I will do, I call this to be knocking out. I am not calling it to be removing it. After all, we need to produce photoelectric effect. We need to produce photoelectric effect. So it's simply not removal. I call this to be extrication. Extrication of electrons, extrication of electrons from the surface of the metal, of a metal, and I would like to read it again. The extrication or knocking, the extrication or knocking of electrons from the surface of a metal, right? Now the question arises, who will knock? Who will knock? The extrication of electrons from the surface of a metal by radiation. So who is knocking here is the radiation. So the extrication or kicking out of electrons from the surface of the metal by radiation is called photoelectric effect. That's the definition. Now we need to explain how this photoelectric effect is basically an application of quantum theory of radiation. Now what is the gist of Planck's quantum theory of radiation is it possesses dual nature. So radiation will be a particle and radiation can be what? A wave. And I told you that this particular photoelectric effect is a direct proof of radiation to be a particle, which we need to explain that in form of an equation. As a science student, we must understand all the statements what you are writing must be converted into an equation. It must be converted into an equation. You must understand. So remember that whatever the statements we are writing, we must be converting that into an equation. Let us convert without delay. But before I rub this, please understand that. So it's a direct. So basically, if someone is asking without any explanation, what is photoelectric effect, then I think in a passive way you must be telling that it's an application of Planck's quantum theory. Second, it's a direct proof for radiation to be a particle. That's a question in your mains. The third thing is, what is photoelectric effect? It's not removal. I make a much effective word. That's nothing but extrication or knocking out of electrons from the surface of a metal by radiation is called photoelectric effect. Now what we will do, we would like to convert this into an equation, and here I convert this into an equation. Observe carefully. Watch carefully here. Now how do we convert this into an equation? And as I told you that you will be having few questions, and you can bank on this, rather not only expecting questions, rather you can bank on these questions, because I'm pretty sure that these will be asked. Now what is this? What is happening? Watch carefully here. Let's convert this equation. Let's convert this statement what I told into an equation. Now remember, and I draw the attention again. I draw the attention of everyone. Radiation, when it strikes a metal, right? Now suppose if this is a surface, and here is a radiation which is striking. Now when the radiation is striking, what does radiation contain? It's absolutely containing photons. Now forget about the packets now. We are no more hanging on to what? We are no more hanging on to packets, right? When a photon strikes the surface of the metal and with some energy, it is striking with some energy, and that's what we call it to be an incident energy. I draw the attention of everyone, please understand, when a radiation is striking the surface of the metal with some energy, that means that synonymously a photon is basically striking the surface of the metal with some energy E, which I call that to be an incident energy. So you strike the surface of the metal with some energy, which is nothing but the incident energy. Now the issue is this incident energy, and I draw the attention again. I draw the attention of everyone. This incident energy is now utilized. I'm a bit slow here such that you can understand properly. So when the photon is striking with some energy, say E, some total energy which we call it to be an incident energy, when it strikes the surface, this energy is used in two ways. This incident energy is used in two ways, 1 and 2. This entire energy which the photon is striking the surface of the metal is utilized in two ways, 1 and 2. And I would like to write the 1, I would like to write the 2, and then we frame an equation which is nothing but the photoelectric equation. You must understand. So I would like to write what I am telling. I'm writing what I am telling. Watch. The incident energy of the photon, say E, the energy with which it is striking, the total energy, is let it be E. And now what I'm telling is this energy is used in two ways. It's used in two ways. One. And I quote one. Partially used to remove electrons from the clutch of the nucleus. And I would like to explain this. When the photon is striking the surface of the metal, and the surface will be having electrons, because after all it's a metal. I am not speaking of a non-metal. When it is a metal, and if you look into the periodic table, the metals are basically placed to the extreme left of the periodic table. Extreme left. And we were told in our schools that from left to right the size decreases. If you ask me what are metals, then out of 115 to 130 elements which are there in the periodic table, metals are those which are having the biggest sizes. And I would like to quote, even the biggest sizes of atoms are placed to the extreme left bottom. When the size of a metal is bigger, the electrons on the surface are loose, because they are not held by the nucleus with such great force, because the size is bigger. So the electrons are basically doing like this. They are relaxing. It's almost like a diffusing of a cloud property. As the clouds diffuse, the electrons are also diffusing like this. So now what's happening? When the radiation is striking the surface of the metal, the electrons which are supposed to be loose and having a diffusing property, what they do, a part of the energy, the part of the striking energy, which is nothing but the incident energy, a part of it is used to remove the electron from the clutch of the nucleus. Yes, of course, you need to do some work to remove the electron from the clutch of the nucleus for the simple reason electrons are bound to the nucleus with some certain force. So if you wanted to extricate the electron, you must be using some energy, you must understand. So when the incident energy is hitting the surface of the metal, a part of it, partially, it is used to remove the electron from the clutch of the nucleus. That's number one. As I promised, it will be used in two ways. The first one is this. The second one, The second one, and I draw the attention and I write it for you. The second one is basically remaining part. Remaining part, as I said, this is partially used, so you have the remaining part. Remaining part used. Remaining part used to give kinetic energy, to give kinetic energy. Because after all, we are speaking that it's a photoelectric effect. It is effect. It's not a passive word, it's an effect. So what you're doing in the first way is you remove the electron from the clutch of the nucleus and you're not leaving it. Then if you just leave it, it's not called a photoelectric effect. So the second part of the energy is basically used to give kinetic energy. Kinetic energy for what? For the extricated electron to produce the effect. You must understand. So there is extricated electron which is available to you because it has been knocked out from the clutch of the nucleus. Now this electron is given a kinetic energy such that it flies off and it produces the photoelectric effect which we are speaking of. So remember that when the incident energy of the photon E, the total energy E, strikes the surface of the metal, then the energy is used in two ways. One partially used to remove the electron from the clutch of the nucleus. Then we are not removing it, it is staying there. Then the remaining part of the energy is given kinetic energy such that it produces the photoelectric effect. You must understand. So as promised, these are all the statements, and as a mathematics student, as a science student, you must understand every statement must be converted into an equation. You must understand here. So before I write the equation, here is what is the gist of what we are telling. First of all, we are dealing with the applications of quantum theory of radiation, that is photoelectric effect. What is photoelectric effect? Is the knocking out of electrons from the surface of the metal by radiation, right? Now, is it a particle nature or it's a wave nature? Of course, it's a direct proof that it's a particle nature. Now, how this photoelectric mechanism is taking place is this: when you strike, the photon is striking the surface of the metal, a part of it is used to remove the electron from the clutch of the nucleus. After all, the electrons are attached to the nucleus with certain force, and if you wanted to remove it, you need to spend the same amount of energy to remove it. Right? That's a common sense. The second thing is the remaining part is used to give the electron the kinetic energy, the fillip, such that it is called a photoelectric effect because you are not removing the electron and just leaving it off. Now what I will do, I will convert all these into an equation. Shall we? Look here carefully now. I wanted to convert all this into an equation. Watch carefully here. Watch. So if you look into this, the photoelectric equation formation. So now I'm actually deriving the photoelectric equation accordingly what we were told in the theory just seconds ago. Watch here. So if you look into the total energy of the photon which is striking it. Total energy of the photon which is striking it. Total energy which is used for energy to extricate electron from the nucleus plus provide kinetic energy to the electron. You must understand this is the sum of both. So the total energy is the partial energy used to remove the electron from the clutch of the nucleus plus the kinetic energy. Now I'm converting this into an equation. Watch here. Now the total energy of the photon is basically partially used to remove the electron from the clutch of the nucleus. Second is to provide the kinetic energy. Now I'm converting this into the basic photoelectric equation. That's nothing but E incident energy of the photon. This is the total energy with which the photon is striking the surface of the metal. Plus. Now this will be used in two ways. 1 plus 2. You must understand. Now this energy required to extricate the electron from the nucleus is basically called, and I call this to be, watch carefully, I call this to be work function. Now what is this work function is? This is the energy partially utilized to remove the electron from the clutch of the nucleus. You must understand. So you need to do some work because the electron is bound to the nucleus. So I call this energy to be work function, where you get some questions on work function, you must understand. Right? Plus the kinetic energy which the electron is provided such that it flies off and produces the effect. You must understand. So it's as simple as that. Total energy is the sum of two things. One is work function and kinetic energy. Further, if you can simplify this, watch carefully here. E, now in sciences, and I draw the attention of everyone. In sciences, especially when you're dealing with radiation, when you're basically dealing with radiation, in sciences, energy has only one equation. For radiation energy, you have only one equation, no two equations. No two equations at all. Don't look here and there for another equation or think about the other equation for radiation. You have only one equation for radiation, and that is proposed by Planck. That's nothing but H nu. That's basically H nu. There is no other equation at all. Whether it's an incident energy or partially used or fully used, whatever, you have only energy equation. That's for radiation. That is nothing but H nu. So I'm not thinking of any other equation. Incident energy is nothing but H nu. H nu. This is proposed by what? Planck. Because E is equal to H nu. That's what he was telling us. E is equal to H nu. That's what he was telling us to calculate the energy of a photon. Energy of the photon is calculated by E is equal to H nu, whether it's an incident energy. So I call this to be what? Incident photon energy, which is equal to work function. Work function is also energy required to remove the electron from the clutch of the nucleus. It is also having an equation H nu. There are no two equations, as I was telling you. So, but this, to distinguish this from this, I call this to be H nu naught. Nu naught. After all, the energy is only partially utilized. Partially, not fully. So naturally what will happen is, this is H nu, this is H nu naught, because the frequency is varying, so the energy will be also less compared to this. This is total energy, this is partial energy. And kinetic energy has the equation half mv square. So I am actually putting this in box for you, and this is what is called the photoelectric equation. This is what is the photoelectric equation, and this entire photoelectric effect is done by Einstein. He has taken a cue from Planck's quantum theory, and the application of the Planck's quantum theory is nothing but the photoelectric effect, which is all this theory is proposed by what? Einstein. And look into this, energy incident is nothing but the work function plus kinetic energy. As we have only one equation for energy, the total energy is H nu, which is equal to H nu naught. Why nu naught? Because the total energy is not used straight away. You must understand. So it is partially used. So the frequencies might vary. And you must understand this is nu naught plus half mv square. That is the photoelectric equation. As promised, you will get 3 questions or 4 questions on photoelectric effect. If this is the photoelectric equation, now what are the questions which you are supposed to get it in JEE mains or whatever exams you write? And I'm telling you with conviction, you can bank on it. You can basically bank on it. So we are so sure that you are supposed to get questions in this. So basically the photoelectric equation, you must remember, is basically the sum of 2 factors. One, the energy used to remove the electron from the clutch of the nucleus, and the second one is the kinetic energy equation, which is nothing but half mv square. Now let us focus on 4 questions which you are supposed to be coming, and you can bank on these questions. And what are these questions? Observe very carefully now. Watch carefully now. Now, what are the questions which you are supposed to get it here? What are the questions? Now, applications of photoelectric effect. Now you can bank on some questions in whatever exams you write. And what are these? One by one I would like to describe. The very first one. Watch the questions expected in exam. The very first question which I would like to write. Now basically, for your understanding, I write the photoelectric equation here for you such that you can constantly refer here. H nu is equal to H nu naught plus half mv square. You must understand. This is the photoelectric equation. That is a photoelectric equation and the applications we are dealing now. Now the very first question what is asked is basically this h nu naught is nothing but work function. Work function. And I find questions in this. It is said it's a function, and in mathematics language it's a function of what? It's a function of what? You say it's a work function, right? So it's a function of what? When I say it's a function of what, on what factors does it depend? On what factors does it depend? That's the first question in exam. You must understand this. Now what exactly is h nu naught and work function? This is basically he's telling energy required to remove electron from the clutch of nucleus. Now if you have a careful look into this statement which is written, energy required to remove the electron from the clutch of the nucleus, then I think you can frame a function. You can actually basically frame a function. It depends on what? So basically remember that we use metals. Now we use metals in photoelectric cells. We don't use non-metals. Because non-metals are placed to the extreme right of the periodic table. So when you move from left to right, the size decreases. It's impossible to remove electrons just by radiation, by kicking the radiation kicks in and the electrons are knocked out. It never happens. And let me tell you even, metals are used in photoelectric effects. The question is, do all metals give photoelectric effect? That's the first question. So we say metals, you have n number of metals in the periodic table. Do we use all metals? All metals, can we kick out the electrons from the surface of the metal? That's another question. And the answer is absolute no. Absolute no. No. All metals cannot be used. So when the photoelectric equation is telling you that the extrication of electrons by radiation, do all metals are involved in this? Absolutely not. Now the question arises, which metals? So remember what is work function? Work function depends on what factors? One thing is ruled out. One thing is absolutely ruled out, that we don't use non-metals, because they are placed to the extreme right of the periodic table. We only use metals. But in periodic table you have a lot of metals. Which metals can be used? So work function basically is nothing but the energy required to remove the electron from the clutch of the nucleus is basically a function of the size of the metal. And size of the metal. So if someone is asking you, you have written work function in the photoelectric equation. It depends on what factors? It depends on the size of the metal. Now if you ask me, do you simply say size of the metal? What exactly is the relation? Then remember, work function, the work function WF is basically inversely related to size. It's basically inversely related to size. You must understand. Now what do you mean by inversely related to size? I write smaller the size, work function or the energy is more. This is unfit for the photoelectric cells, because please understand that when the size of the metal is small, so where are metals in the periodic table? Basically, they are placed to the extreme left in the periodic table, and when you move at the middle, you have transition elements. So you have a lot of metals. Don't go to the extreme right. When you go to the extreme right, you have mostly non-metals. So metals are there to the extreme left and to somewhere at the D block. You must understand that. So do every metal is used in the photoelectric cells? Absolute no. And so what I'm telling, smaller the size, the work function is more, this becomes unfit metal. And these are not used in the photoelectric cells. These are absolutely not used in the photoelectric cells. You must understand. So now, which metal is used? Now, bigger the size, and I quote, these are the metals which are used in the photoelectric cells, and that is the question in the exam. And I draw the attention of everyone, This is the question which we will be asking in the exam. You must understand, bigger the size, the work function is less. And let me tell you, the biggest metals in the periodic table are to the extreme left. That is the first group elements, or I call them to be alkali metals. And in alkali metals also, not all alkali metals can be used in photoelectric cells. Not all alkali metals can be used in photoelectric cells, because we were told in a group from top to bottom, the size increases. So we require a metal. Now what are the conducive conditions? Now what are the conducive things? First of all, for usage in photoelectric cells, not everyone can be used. You have 130 elements in the periodic table. Not everyone are used. Very few, 2 or 3 elements are used in photoelectric cells. You must understand. And that is usage in photoelectric cells. First of all, the size of metal must be bigger. And that the work function must be small. Then this will produce the photoelectric effect, because when the size is bigger, the electrons are far away from the nucleus. I think we are easily able to remove the electron from the clutch of the nucleus. Otherwise, you will struggle. Now, what's a direct question in the exam is, remember that it is only, and I quote, it is only potassium, rubidium, and cesium. These are the 3 metals used in photoelectric cells, and this is the question in exam. That's the question in exam. Why only potassium, rubidium, cesium? Because these 3 elements are placed to the extreme left of the periodic table, and not only extreme left, they are placed to the extreme left bottom of the periodic table. And when you are placed to the extreme left bottom of the periodic table, it's easy for the radiation to knock out the electrons. And the work function will be lesser. So there are absolutely only 3 elements in the periodic table which are used commonly in photoelectric cells. That's nothing but rubidium, potassium, and cesium. You must understand. Right? And also let me have a quick recap of what we are doing. That's a photoelectric equation. And the first question, you will get it in a work function. Work function depends on what? Work function basically depends upon the size of the metal. And the conducive things are, the usage in the photoelectric cells is the size of the metal must be bigger. Then the work function will be smaller, and I think then you are able to remove the electron from the clutch of the nucleus. Forget about all these things, and remember basically that it's potassium, rubidium, and cesium which are used in photoelectric cells. You must understand. So that's question number 1. So work function basically is a function of the size of the metal. So bigger the size, better conducive to use such metals in the photoelectric cells. And how many cells do we actually remember for 10-20 elements? Absolutely not. The most commonly used metals in the photoelectric cells are basically nothing but potassium, rubidium, and cesium. These are placed to the extreme left in the periodic table, and they have the biggest sizes. So when you have the biggest sizes, the electron is basically doing some relaxation from the clutch of the nucleus, and it becomes easy for the electrons to be knocked out by the radiation. That's what is the intent is. So work function depends on what? Work function is nothing but synonymously is nothing but the energy required to remove the electron from the clutch of the nucleus. And for that to be conducive, I think you need to choose a metal which is a common sense, which has a bigger size. That's question number 1. So there are 2 questions which I told rather. One, basically applications of Planck's quantum theory is basically nothing but the photoelectric effect. That's number 1. Number 2, photoelectric effect is basically direct proof that radiation is a particle, because we were claiming radiation can be a wave as well as a particle. You must understand. So basically, photoelectric effect is a direct proof that the radiation is a particle, right? And the third, there is another question. And I'm telling you, this is very, very important. V power n important and n tends to infinity. It's extremely important. It's basically extremely important is this question which I'm now quoting. Watch carefully here. Watch, and I draw the attention of everyone. And here to the right, I have written the photoelectric equation for you. That constantly you can view it. Right? Now, what is the second equation? Watch. One photon. And I want everyone to visualize this. One photon kicks only one electron. Let's understand. As radiation is a shower of photons, according to Einstein, one photon, when it strikes the metal, it will kick only one electron. One photon kicks only one electron. And I quote again. One photon only kicks one electron. Knocks out only one electron. If that is the case, then two electrons knock two electrons. If that is the case, then 10 electrons knock 10 electrons. If that is the case, then 100 electrons knock 100 electrons. Now what is this? So first of all, understand that one electron will knock out only one electron. One photon will knock out only one electron. Now what is this, sir, you have written on the board? If you ask me, then watch the increase from 1 to 100. And I draw the attention, please. The increase of 1 to 100. Now the increase of one photon to 100 photons. In sciences, this increase of number of photons, those are striking the surface of the metal. This is what we call intensity. That's what is called intensity of radiation. You must understand. So what is this, sir? From increasing of one photon to 100 photons, 1000 photons, because one photon will only kick one electron. This increase of one photon to 100 photons is basically nothing but the intensity of radiation being increasing. Increasing intensity. Well, I would like to give a live example for you. Now remember that when we used to play with a magnifying lens, in our childhood we used to sit in the ground and our friend was reading a newspaper or reading a book, right? We used to have a little bit of sadism with us. So what we used to do is we have to take the magnifying lens here, and I think we put it under, you face the sun like this, and I think your friend is not seeing. So then what is happening is, I think he is basically, that light has been put at the thigh. So suddenly what happens is he screams with pain because you are actually burning it. And I think earlier also, if you see, we used to burn newspapers with the magnifying lens. Now why? If you just take a newspaper and sit in the sun, it doesn't burn. But if you put under a magnifying lens, it burns. What was the first case? The first case was the number of photons that are striking the newspaper are very, very less. But when you put a magnifying lens, then the number of photons that are striking the newspaper increase, and the sum total of all the energies of all the photons striking the newspaper will be higher, hence it burns. Simply if you open the newspaper and sit in the sun, nothing happens, because the number of photons that are striking the newspaper or the particular area is fixed. Now what happens when you actually increase through a magnifying lens, then the sun passes through the magnifying lens, then I think the number of photons that are striking the newspaper increases, and the sum total of all the photons will be much higher. That rises the temperature, and hence the newspaper burns. This phenomena is nothing but what? Increase of intensity. This is what exactly happening here. This is what exactly happening here. Watch. One photon will strike only one electron out. 100 photons will strike 100 electron out. If someone is asking what is this increase of 1 photon to 100 photons, then I call this to be intensity of the radiation increasing. Intensity of the radiation increasing. So that's what is called intensity. Right? Now why am I telling this? Why am I telling this? Now watch here. That's about the photons. That's about the photons. From 1 photon to 100 photons, you are increasing the intensity. Now what is happening to the electrons? What is happening to these electrons? Now remember, suppose if you are striking 100 photons are striking the surface of the metal and you got 100 electrons out. What is strange here? What is very strange here? What is very strange here is if 100 photons are knocking 100 electrons, surprising, all these electrons have same kinetic energy. Same kinetic energy. Now two things which I wanted to write it very clearly. Watch here. So the very first one, intensity increase. Intensity increase. That is, number of photons striking a unit area increases. Suppose if your intensity is increasing, then only number of electrons kicked out increases. So if you are increasing the intensity, the number of photoelectrons increase. Just the number increases. But remember, second point, the kinetic energy of these electrons knocked out remains the same. You must understand. Remains the same. So what I mean by this, just increasing intensity will increase number of electrons and not kinetic energy of electrons that are ejected. So you are knocking out n number of electrons, but all the electrons' kinetic energy will remain the same. You don't celebrate just because you have increased intensity, the kinetic energy also increases. You are mistaken. No. Only the number will increase, but the kinetic energy will remain the same. You must understand. Now, people will ask me, what to do to increase the kinetic energy? Now remember, here is a small diagrammatic representation which I am quoting. Here is the surface of the metal, and a radiation is striking with a frequency mu. That's a fixed frequency mu. That's not changing. That is not changing. But if you put a magnifying lens here, number of photons that are striking the surface will increase, and the number of electrons that are ejected also will be in the same in number, but the electron's kinetic energy will remain the same. So student will ask me, so what to do, sir, to increase the kinetic energy of the electron? So now I quote, and I put this in box here for your understanding, that alta or altering frequency alters kinetic energy and not intensity. You must understand. It is basically altering frequency which will change the kinetic energy and not the intensity. You must understand this. These two questions are questions in the exam, beyond any doubt. So what I will do finally, I want to list out all the 5 questions which will be asked in exam. Shall I? Watch carefully here. Watch carefully. I want to put all these things in place at one place. Watch. I am putting all these things in place before I actually conclude this subtopic. Watch carefully here. Now, what are all the questions which are asked in exam 1? All questions at one place. 1. Photoelectric effect is application of quantum theory of radiation. That's number 1. That's the very first question. Second, 2. Photoelectric effect is direct proof radiation is a particle. Of course, the photoelectric effect is a direct proof that radiation is a particle. That's second question. Third question, the photoelectric equation. That is H nu is equal to H nu naught plus half mv square. Well, I would like to tell the students in an easy way, any science equation which has kinetic energy, like half mv square, any equation which has half mv square represents mechanical motion, and any mechanical motion is a proof that particle nature. There is no second thought in it. So from now onwards, when I open a textbook, when I see an equation which is having a kinetic energy, then I'm sure that it's nothing but a particle nature of the radiation. Absolutely no second thoughts. So you can see here half mv square, then put straight away that it's a direct proof that radiation is a particle. That's number 3. Number 4, intensity increases, number of electrons increase, and not kinetic energy. 4, 5, alter incident frequency, kinetic energy alters. And 6, work function is inversely related to size. And 7, potassium, rubidium and cesium are used in photoelectric cells. You must understand this. Right? So you go through all this. These are the questions, and I think you understood the photoelectric effect, which is very much you must bank for the examinations. You must understand. Right? And what we will do, as I appeal to the students, you must follow me. Every day you must follow me and subscribe to the channel such that you can get some alerts. Remember that what we are doing is, I want the students to focus on your mathematics and physics. Chemistry, you leave it to me. Because I'll be doing this in a sequence. Like we started atomic structure. Yesterday I was telling you the quantum theory of radiation. Today it's an application of the quantum theory of radiation. As I told you to bank on me for chemistry, because I think here are the questions. Other than this, you won't get any questions in photoelectric effect. You must understand. Right? Then the third, tomorrow in the next class. So not tomorrow, next class, when you are following me in a sequence, I think we will be discussing something about Bohr's theory for atomic structure, and I will tell you what exactly we are doing in atomic structure. The aim for this chapter, let's slip on to that, where we have a lot of equations to be written. Thank you very much. You must be waiting for me for the next class. Please follow, because at the end of the subtopic or in between subtopic, I'll be quoting questions for you. Thank you very much.